Our speaker is Senia Sheydvasser from Bates College in the warm state of Maine, who will speak on Ulam sequences. Please.
All right. Well, thank you very much. A little bit of prehistory here. Um, in terms of where all of this comes from. So this in 1964, Ulam published there's a book and a paper, and both of them mentioned a particular sequence of integers, which we now refer to by his name. What he suggested was build a sequence as follows. Take the first terms to be 1 and 2, and then every subsequent term should be the next smallest integer that can be written as the sum of two distinct prior terms in exactly one way. So this sequence begins like this. It goes 1, and then 2, and then 3 is 1 plus 2, and then 4 is 1 plus 3. But of course, we skip 5 because 5 is both 4 plus 1 and 3 plus 2. So we have to go over to 6. 6 is fine because that's only 2 plus 4. And we skip 7 because 7 is 6 plus 1 and 4 plus 3. So we go on to 8, which is 2 plus 6. And okay, and we keep going like this. Right? And he asks this question of, well, how would you determine the growth rate of this sequence? What is its density and the like? This is still like a very open question. To the best of my knowledge, the best bound that we have is that the sequence can grow faster than the Fibonacci sequence. But all of the numerical evidence tells us that it actually grows linearly. So there's a pretty big gap between exponential and linear in there. And then, he wrote this down, and for about 50 years, no one really thought about Ulam sequences very much. But, a few papers here and there about it. But like all of the modern interest in it, maybe before that, there were a few generalizations. So people considered these sequences, which I'll denote as U of AB, where it's exactly the same definition, except that you change the starting condition. Rather than asking them to be 1 and 2, you say, well, I take two integers, two positive integers, A and B. But it's the same rule that every subsequent term is the next smallest that can be written as the sum of two distinct in exactly one. Right? There were, there's some results about this, about when such things are quite periodic, when the consecutive differences of terms are periodic. Anyway, then there's a bit of a renaissance in 2015. Stefan Steinerberger comes along. He was decided to apply some ideas from Fourier analysis to the Ulam sequence, and he found what has been termed a magic number for the Ulam sequence. I'll write this as lambda 1 comma 2, which is about 2.44344. We have no idea, there's like no closed form expression for this. We have no idea like really what this thing is, whether it's rational or irrational, anything like that. But here's what you do. You take the first n elements of the Ulam sequence, modulo this number, and then you take a histogram. Now, of course, lambda is, we only know that it's real. It could be irrational. So you might well ask, what do I mean by taking it to mod lambda? Well, all I mean is that I take, I add, subtract integer multiples of it until I am in the range between 0 and lambda. So as an example here, I wrote out like, I need to compute out 5.1, not 2.4. What do? I subtract off multiples of 2.4 until I get something positive but less than 2. Anyway, take say the first what is it? It's a little cut off for me because of Zoom. But, the first 10 to the 4 terms of the Ulam sequence. Consider it modulo this lambda and plot the histogram. So what's going on here is the length of the bars are how often you get a residue in like this little tiny interval there. So this is going from 0 on the left-hand side over to lambda on the right-hand side. And you notice that the whole thing, I mean, first of all, it's bizarre because there's these two peaks, but secondly, the whole thing is concentrated in the middle third of the interval for some unclear reason. Okay.
So surprisingly, the answer in general, well, that's what it's complicated. And
there seems to be audio coming in from, okay. So this was in Stefan's original preprint with the first 10 to the 4. Then we have much better data now. So this is the first 10 to the 10 terms. So this is the middle third again. So on the left-hand side, we have lambda over 3. On the right-hand side, we have 2 lambda over 3. And in the middle, we have this weird distribution of some sort. What is this distribution? I don't know. No one knows. There's evidently there's some kind of hidden signal in the Ulam sequence. We have no proof of this. We only have numerical evidence for this.
Do you have a sense for how smooth it is? That is to say, if you take too small a resolution, then the fact that you're taking a finite number is going to show up. But the question is, I mean, in the limit, do you think it's a smooth? Do you think it's bumpy, fractal?
I think, and I don't have a proof of this or anything like this, but my sense is that this seems to be a smooth function. This is a smooth probability function. But the only thing that I can base this off of is that, well, we've computed trillions of terms, and it sure looks smooth. That's about the best that I can do. Like, we don't know what this distribution is at all. I've never seen it before. If you have ever seen a distribution like this, let me know, or let Stefan know. We will be absolutely delighted to find out what is this after all.
I mean, if you just did the distribution modulo 2.44 instead of 2.44344
Yes.
something, would it make any difference?
Yes. Eventually, it would become uniform. I mean, this is like a general theorem of Fourier analysis, that if you have a sequence, you consider the residues mod lambda for a randomly selected lambda. With probability 1, you will get the uniform distribution. So, you might not be able to detect this for the first, 1,000 terms. But once you get out to 1,000,000, 1 billion terms, you'll start losing the structure of this distribution. So in fact, so how do we compute this lambda nowadays? We compute millions. We compute many terms, and then we fine tune it until we see the distribution showing up in the middle third as we expect. Yeah, and there's, as I said, there's just a lot of numerical evidence for this. Judson and Gibbs, they've done a lot with this. I will note as well that this does not seem to be something that was only true for the original sequence with starting with 1, 2. For example, you take the Ulam sequences starting with 1 and n, wherein there's some positive indices. There seem to be similar magic numbers for that as well. And there's probably others for other families. So let me show you some of this. So these are some of my own pictures of this. This is with, I forget, the first 100,000 terms, something like this. So this is the picture for U14. Okay? You have, again, it's completely concentrated in the middle third. And this is U15, U16, U17, U18, and U19. right? It's all very, very similar, except where we seem to be multiplying the number of peaks there. Okay. So Stefan comes up with this, and immediately people are thinking, well, my God, there's something very special about the Ulam sequence. Can we learn more about this? Can we figure out why this magical thing is true? And there's been a lot of papers since then looking at like various generalizations and analogs. And a lot of them were actually co-authored with undergraduate students. So in particular, in 2018, this is how I was introduced to the Ulam sequence. I was running a project for summaries, Yale's like summer research research for undergrads program, and I needed a project. I needed a topic for it. And, Stefan was a postdoc at Yale at the time. He was a friend. He still is a friend. He said, well, you should look at the Ulam sequence and see what you can discover with it. So I had 3 students that summer. It was Josh Hinman, Boris Kukan, Alexander Schlesinger. We ended up co-authoring 2 papers. What I wanted to tell you a little bit about today was one of the things that we discovered on the kind of more recent progress along these lines. So let me set the scene for you. Right? I came in every day to meet with my students, discuss what's been happening. And this particular day, I come in and see that all of them are working on the blackboard. They have a picture something like this, where they're writing out terms of Ulam sequences U1N, but with a little bit of a twist. So what they did is that they grouped up terms that were like consecutive. So and U12 and U13 don't really seem to want to play by the same rules, but U14 onwards, what you see is that you get initially you get always 1. That makes perfect sense. Then you get everything from n up to 2n. So 4 up to 8, 5 up to 10, 6 up to 12. Then there's a jump. You have 10, 12, 14, 16, 18, then 16, 20, 24, 28, 33. And then again, you have a block of consecutive terms. Okay, and then you have another collection of singletons, and so on. And what basically they told me is, oh, well, what it looks like is that if n is at least 4, here's the structure of the Ulam sequence. It goes 1, then n up to 2n, then it's 2n plus 2, then it's 4n, then it's 4n plus 2 up to 5n minus 1, then it's 5n plus 1, and so on. And I looked at this, I was just like, there's no way that this can possibly be true. How can it possibly be that if you know 2 Ulam sequences, then you can predict what's going on for all of the rest of them, right? Because you only need 2 in order to be able to work out what these coefficients are, because it's an affine function. There's just exactly 2 degrees of freedom. But I dutifully went home, wrote some code, tested hundreds, thousands of examples, and I became convinced that, oh my God, yes, this is true. So we ended up with the following conjecture, what we've since called the rigidity conjecture. That there exists some big N, which is almost certainly 4. And these integer coefficients, AI, BI, CI, DI, such that if n is bigger than this capital N, then what is the structure of U1n? It splits as a collection of intervals, consecutive intervals, where the endpoints of these intervals are given by affine functions. So it's starts with I have this entire block starting from AIN plus BI all the way up to CIN plus BI. Then I have the next block, then I have the next block. And of course, I impose this condition that CIN plus BI plus 1 has to be less than AI plus 1 and plus BI plus 1. So to make clear that these are consecutive blocks and that they don't intersect.
Don't intersect, and they're never, I mean, they never sort of merge. There's always a space of at least one between a block and the next block.
Exactly. Great. Now, this is still open. It is stated in this kind of generality. But we do have some interesting partial results. So the first thing that we have, right, we prove the following, that there exists integer coefficients, AI, BI, CI, BI, such that choose any integer k, there exists some big N depending on k, such that for any n bigger than n sub k, if you look at the first k blocks, they match this theoretical prediction, right? So this is pretty much exactly the statement from the previous slide, except that now our big N depends on how far out we're going, how many of these consecutive runs we've considered. Okay? So in particular, if we could prove that this bound n sub k does not actually depend on k, this would be the rigidity condition. We would have proved it. Unfortunately, it is entirely possible that n sub k just grows as a function of k off to infinity, which makes rigidity never quite kicks in. Now, I presented this at in fact at the seminar. I don't know, 4 years ago, 5 years ago, something like this, I think. And at the time, the proof that we had used model theory. We did this using a non-standard model of arithmetic, which worked, but I was unsatisfied with this because it did feel like we were kind of getting something out of nothing. We had the discussion before the start of the talk about how a proof should make things more clear rather than obscuring. And this was precisely the point. I wanted a proof that would make clear exactly what was happening. So just a few years ago, I finally came up with a way to do this constructively. So what we're going to do is we're going to construct another analog of the Ulam sequence, but in a different set. Specifically, we're going to consider polynomials ax plus b with integer coefficients. Right? So this naturally has a group structure, it's a abelian group, but I actually want to give it the structure of an ordered abelian group. I want to give it the lexicographical ordering, right? Where if I need to compare two of these polynomials, I first check the leading term. If the leading term, if I have ax plus b and cx plus d, if a is bigger than c, then ax plus b is bigger than cx plus d. I don't even need to look at the lower terms. Or alternatively, if a is equal to c, then I check whether b is bigger. This is the idea. Like checking alphabetical order. Now, what we're going to try and do is we're going to define what an Ulam sequence is inside of it. Now, initially, this seems like, oh, maybe we can do this just copying the definition because it's an abelian group, so we can talk about addition, and it's an ordered abelian group, so we can talk about elements being smaller, larger. But there's a little bit of an issue because the positive elements of this abelian group are not well ordered, right? So for example, I can go down x minus 1, x minus 2, x minus 3 indefinitely, and there's no minimal element. So when I try to talk about the smallest element satisfying such and such condition, there's a little bit of an issue, because I have no guarantee that a smallest element even exists. Okay? This is not necessarily well defined. What my idea was that, well, what we can do is we just need to salvage enough of well-orderedness. We don't need to make this thing well-ordered. We just need enough of it to be able to make the proof go through. So this led to the following definition. Okay? So you take two polynomials, A and B, of this type, and then you say that a Ulam sequence, starting with these polynomials A and B, is a set U of such affine polynomials with satisfying the following three conditions. One, that it starts with A and B, that if I take the intersection, if I look at all elements at B and below, I only get A and B. So there's nothing between A and B, there's nothing before A, nothing before B. That's the first. The second thing, and this is salvaging just enough of well-orderedness here, is that I ask that if I have two polynomials P and Q, and I intersect my set U with the interval of things between P and Q, then that set has to have a minimum and a maximum, right? So even though the full set of integer polynomials is not well-ordered, I do still have something like well-orderedness here, because if I look at an interval, I get a minimum. And the last thing is exactly what you expect, like this Ulam condition. If I take one of these polynomials, when is it in the Ulam set? Well, exactly if and only if it is the smallest element in this set of polynomials which are larger than the Ulam, the terms in the Ulam sequence below below my polynomial P, such that there exists exactly two distinct prior polynomials in the Ulam set, such that if I add them, then I get this polynomial. It's you have to be careful about how you state this. It looks a little bit weirder, but it's still the Ulam condition, just phrased a little bit more precisely to make clear that we don't really need well-orderedness for this. So what you can prove is that regardless of which polynomials you select, there will always be an Ulam sequence with those starting conditions. Now, the only thing is that unfortunately, it's not unique. In general, if I choose polynomials A and B, there might be two different ways, or three different ways, infinitely many different ways to build out this set. And maybe that's just because I haven't given the right definition. Maybe there's some conditions that I've missed. Who knows? But I will say that at least for some A and B, you do get a unique Ulam sequence. So here's a simple example, well, simple-ish example. Consider the Ulam sequence starting with x and x. Right? Then you get a completely uniquely defined Ulam sequence. So it goes x plus 1, then 2x plus 1, which is x plus 1, then it's 3x plus 1, which is x plus 2x plus 1. All right, and so on. It's very similar to the usual Ulam sequence. You just get these the sequence of affine polynomials. A more interesting example is what happens if you start with 1 and x. So you can do the following here. So what do you get? You get that it'll be the following union of intervals. It goes 1, then x to 2x, 2x plus 2, then 4x, 4x plus 2 up to 5x minus 1, 5x plus 1, etc. This might look very familiar. This is exactly what we had for the Ulam sequence starting with 1 and f.
Yeah,
This is not a coincidence. Oh, yes, ma'am?
checking, when you say x to 2x, that's an infinite set, in fact, here, right?
Yes, it is, yes.
I mean, that's part of the point here. It's meant to, okay, yeah.
Mm-hmm. Yep. So you can do, there's an easy induction argument to show that this really is uniquely determined, that as soon as you say that it starts with 1 and x, everything else is completely determined, and that it is of this form, that there exist integer coefficients ai, bi, ci, di, such that you have a decomposition of this set into consecutive blocks of intervals.
How close is this to your original non-standard proof? I mean, is x sort of an infinite element?
Yeah. One way to think about this is that we took our non-standard model of arithmetic and then kind of took out everything that was unnecessary. We don't need the whole non-standard model. We just need everything generated by 1 and this one non-standard integer. That's a completely valid way to think about it, but it's just a little bit cleaner. And the nice thing is that phrasing it this way, well, I'll get to it in a second, but there's an algorithmic way to do all of this, which was not evident in the model theory.
Yeah, just one more check. The interval from x to 2x, it's got 2 sequences in it, right? Going from x plus 1, x plus 2, and so on, and going down from 2x to x minus 1 to, right?
Yes.
Okay.
Yes. So in fact, so let me give you just a little bit of the proof, which this will make this explicit. So we know that the set starts with 1 and x. Okay, great. Now from this, we can conclude that it includes x plus 1, x plus 2, x plus 3, because of course, x plus 1 is the smallest polynomial that can be written as the sum of these prior terms. It's 1 plus x, then x plus 2 is plus x plus 1 plus 1, x plus 3 is x plus 2 plus 1, and so on, right? And it can't at any point be that there's 2 ways of summing it up, because if we don't include, if the only way we could get another one is if one of the summands wasn't 1. But if one of the summands wasn't 1, that means that both of them have an x in it. And if you add x and x plus 1, already you're looking at 2x plus 1, which is much too big, right? Okay, well, here's where the intersection with an interval becomes important, because if I didn't have this, then I could just say, oh, well, this is my Ulam sequence. It goes 1, x plus 1, blah, 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 blah. But I say, no. I know that if I intersect this set with the interval from 1 to 2x, it has to have a maximal element, by definition, of what an Ulam sequence is, right? So write it as 2x minus b, right, for some non-negative integer b. Now observe that, first of all, if 2x minus b is in the set, then it had to have been that 2x minus b minus 1 was in the set, because 2x minus b has to be a sum of 2 distinct prior terms. And the only possibility is that it was 2x minus b minus 1 plus 1. And okay, all right, by that same token, it had to be that 2x minus b minus 2 was in the set. And 2x minus b minus 3 was in the set. Just going down. Okay. So we can starting from the top, we can turtle downwards. On the other hand, right? Suppose that I know that it contains 2x minus b. Well, then I have to include 2x minus b plus 1 and 2x minus b plus 2 and the like. Why? Because Well, I can always take 2x minus b and add 1 to it. So that's a sum of two distinct prior terms. The only thing I need to fear for is whether something like 2x minus b plus 1 can be written as a sum of two distinct prior terms. But the answer is no, because the smallest thing that could be is 2x plus 1. So I have to get everything up to 2x. And now, on the other hand, I don't contain 2x plus 1, because on the one hand, this is 2x plus 1, and on the other hand, it's x plus 1. Okay, so we've written it down as a sum in two distinct ways. So that has to be skip. Right? So what we've managed to show is that the first two blocks have to be 1 followed by everything from x to 2x. Now the question is, okay, well, how do you proceed from there? The idea is that you work recursively, right? At every step, you've added on one of these blocks. And now to get to the next bit, you just think about, oh, okay, the next bit has to be coming from me taking this block and adding it to previous ones. Well, I mean, okay, you need some rules for how to add these things together. You need a few different subroutines, but in principle, you can actually just write down an algorithm to do it. So you can write down a polynomial time algorithm where you give it a k and it computes for you the first k coefficients, ai, bi, ci, di, such that these are the coefficients used in this Ulam sequence over the polynomials. Its running time, I think, is something like k cubed log k, something like this. Simply because you have to iterate over all of the previous intervals and just keep doing this over and over. And there's some amount of search that, like binary search, that has to occur where the log k comes from. Yeah, I've actually sat down and implemented this algorithm in Python. It does work. Now here's the really fun part. I have this algorithm. I claim that I can modify it such that I can compute this integer n sub k from our original theorem. This is this integer n sub k such that for all little n bigger than n sub k, the first k intervals of u1n are exactly the ones from this theoretical prediction. Sorry.
Yeah, but you're not computing the nk, you're computing some nk, which presumably is not optimal because you think the optimal is 4. Regardless.
Yes, this is true. This is true. That's right. That's right. I mean, to be fair, you can figure out what the optimal one is for a particular k, because as soon as you have a bound, you can just check the Ulam sequences below that bound. And that way you can get the optimal.
And you verify that it's in fact 4 as far as you can compute.
Exactly. Exactly right. Exactly right. Yes. So yeah, this is this beautiful idea that you can just plug in a particular n for x, and everything still works somehow. So how does this work? Well, here's the thing. How does this algorithm work? What sort of steps does it have? Well, we're adding things together. That's fine. When we add affine polynomials, it doesn't matter whether we evaluate x to something. That's not going to change the result, right? Because we have a group homomorphism, if you like, from the integer polynomials to the integers, all as well. The problem is when I have comparisons, right? I have comparisons. I take two polynomials, ax plus b, cx plus d, and I need to say which one is larger, which one is smaller, in order to understand like in what order to put these blocks in, essentially, and like when do they intersect. But here's the thing: if x is large enough, then this comparison will be still true, right? If what I mean is like suppose that it is the case that I compare these polynomials and I find that cx plus d is bigger than ax plus b. Well, if x is big enough, then when I plug in a large enough integer for x, this is still true. On the other hand, if I'm only computing some finite number of intervals, we've only have these finitely many comparisons that we've done. So just figure out the integer that you need such that for all larger intervals, all of these comparisons still go through just fine when you plug in. Well then, okay, that's your n sub k. If you take a larger n, then you're guaranteed that everything is, the algorithm will work exactly the same way if you were doing this with integers as opposed to integer polynomials, right? Now, unfortunately, I should note this. In practice, this algorithm isn't very efficient. I've run it, but A, it takes a very long time, and B, the bounds that it seems to give are not very good. I've managed to show that n sub k has to be no more than 10, say, this way. But it does feel like it's growing as I compute more and more intervals. Which I don't know whether that's whether eventually it stops growing, or what this tells me is that I'm not using a very good algorithm and there's like some different technique that I should be doing that maybe uses some special properties of these coefficients. And if I did this the right way, then it would go through just fine. But there's another way that you can do this. Because it turns out in practice, these coefficients have a very, very special growth property, which I will discuss in a second, which you can use in an absolutely elementary way. Basically, what you show, it's something like if rigidity holds for the first, I forget, like 15 Ulam sequences, like you compute the first k intervals for the first 17 or so, then actually it has to keep going. And so using this kind of idea, I managed to prove the following, that the rigidity conjecture holds with n greater than or equal to 4 for the first 217,529 intervals. Now, you might well ask, why this weird number? why is it 217,529? And the answer is that's the point when my code crashed. So I was able to salvage it at that point and pull out the data that I had there. But this is why it wasn't like a nice round number. I think the original goal was to try and get to 500,000 or something. But just didn't quite manage to do it. And I should note that I'm pretty much convinced that there has to be a better way to do this. So I noted that Gibbs and Judson, they computed trillions of terms of the U12 sequence. I think that it should be possible to modify their algorithm to work certainly for U1n, but maybe even for U1x for polynomials. And if we can do that, then we would be able to get better data, maybe actually be able to check this for billions of intervals and see whether everything continues to be true. At this point, I'm convinced that it is true, but you never know. You never know. Okay. Now, in terms of what do I mean when I say special properties of the coefficients? I mean, maybe kind of leave off on this. I do want to leave a fair amount of time for questions because experience tells me that there's usually many with talks about the Ulam sequence. These coefficients seem to be just incredibly strong. So in particular, so for these first 200,000 something intervals, I was able to confirm that the following is true, that there is a strong, very strong linear relationship between AI and BI and CI and DI. Very specifically, if you plot one against the other, then it is essentially a line with slope B, where B is about 0.1391. And the
I'm guessing you
error,
have no idea what that coefficient is, right? What that number is.
no idea. No idea. It's you get it by linear regression. But I have no idea whether it's rational, irrational. There's no closed form for it. But yeah, the error is tiny. It's less than 2.5 across the whole thing. And I used to, when I used to give this talk, I used to include a slide where I would draw the graph of AI against BI, CI against BI, and then I realized that there was no point. I was just drawing two lines. You know, you can't tell the difference with the naked eye. It's just impossible. So it's pointless. But I will say the fact that this was known to us back even in 2018. We conjectured that this was the case. We just didn't have as strong evidence for it at that time. We were dealing with like thousands of it, as opposed to hundreds. But we're fairly sure that this just holds true for all of the coefficients. It's always this very strict linear relationship. And I will note that there is one apparent connection between numbers that I've thrown around in this presentation, which is the following. Consider the magic number for U1n, right? This is, I think to be consistent with my prior notation, should have been lambda 1n, but if you will forgive that. If you compute what this is, what you discover is that it is approximately 3n plus 3b, where b is the slope of these lines. So what's happening is that there's a magic polynomial for the integer polynomial set. So if you look at the polynomial 3x plus 3b, you can, with some finagling, define what it means to take your Ulam sequence starting with 1x modulo this polynomial. And what you discover what this means in practice is that it means that there's a congruence restriction on these coefficients AI, BI, CI, DI, mod 3, which holds almost always. It's like some very, very small amount of exceptions. And then you also have this the 3b captures the fact that there is this linear relationship between the coefficients describing the beginning of the interval and the coefficients describing the end of the interval. And the fun thing about all of this is that if we could prove these properties, these structural properties of the coefficient, and the fact that you can just plug in for x and just get the Ulam sequence, then we would have proved this conjecture that Stefan has. Not for U12, but for U14, U15, U16. Which to me seems like the first time that we've actually had any kind of route towards proving something like this. Maybe I'm being a little bit too optimistic there, because proving that these coefficients actually have these properties is also completely open. Who knows? But I don't know. To me, it feels like closer to mathematics than I know, as opposed to this two-modal distribution in the middle. Who knows? All right, I think I'm going to end here and open up the floor for questions.
Thank you very much. Questions for Senia?
Yeah, so you mentioned this Gibbs-Judson algorithm.
Yes.
Yes. So they didn't just let it run longer, they had some other way of computing the Ulam sequence. Is that right?
That's right. So they do this in a clever way. So they make use of this magic number because their observation was that if we know that pretty much everything is in the middle third of the interval, right, with very, very few exceptions. On the other hand, if you take two elements in the middle third and add them together, then it forces you out of the middle third. What that means is that almost always the next term in the Ulam sequence has to be in the something from the middle third plus something outside of the middle third. So rather than just storing the terms of the Ulam sequence like consecutively, they store them in bins, modulo this magic number. And what this allows is that it allows them to find the counter examples to say two prior terms adding up to a new one much faster. Because basically the way that they search for them is they've shifted it around. So they find counterexamples much faster. And once you found a counterexample, that's it. You don't need to keep searching. Now, of course, we have no way of proving that their algorithm is actually faster, asymptotically. We observe that in practice. If we could prove that this magic number really was magic, yes, then we would be able to do it. But it is conceivable that it happens to be faster for the first 10 to the million terms, and then after that it becomes glacially slow again. Who knows?
Other questions?
Yeah, there's a spectacular result from the 70s due to Ehrenfeucht that says that the class of exponential polynomials is well ordered. So what's an exponential polynomial? You take one, you take x, you close it up under addition, multiplication, and exponentiation. Given p and q, p to the q is in there. And it's well ordered under eventual domination.
Interesting.
and- yeah, so it's quite a difficult theorem. Uses the theory of well quasi orders, which is also really interesting. And there's an old conjecture that precedes this due to Skolem, about the order type, because if you've got a well-ordered set, you can classify the order type. So what's the order type of the set? And this is still open. But there was some work done on it, maybe in the 80s, maybe still in the 70s, by a guy at Florida State. His name is Hilbert Levitz, who used some non-standard techniques that are very, very similar to the kind of arguments that you were making, looking, weigh things add and subtract and sort of poking in to see where they can come from. And so, for me, this raises the question of whether there's a relationship. I mean, obviously, you can create these Hilbert sequences now in the class of exponential polynomials. But it feels like somehow that there might be some kind of and maybe it's just phony. Maybe it's just one of these things that looks like a relationship, but it feels kind of yeah. No, this result of Ehrenfeucht's is
Interesting.
every so often I look again at the proof and I say, this is just spectacular.
So when you say closed under exponentiation, how should I think about this? Is this like a formal sequence type of thing where I think of e to the x as being 1 plus x squared over 2, that kind of thing, or?
Yeah, well, it's not. It's no x squared over 2, right? There's no that. It's just it's just positive stuff. So it's just addition, multiplication, and given. So you might have 2x squared to the 3x plus 1, and the fundamental idea of the proof has to do with the fact that you can turn these things somehow into finite trees. And once you do that, the collection of finite trees is well quasi-ordered. That's a result of Kruskal's, which again is very deep. It's a deep result that's provably deep in some sense. Yeah. So these things are all you don't have subtraction. So that's one difference with the kind of argument you were doing. You don't have 3x minus 1, though if 3x minus 1's in there, then so is 3x.
Right.
But
right.
So some of the stuff you've got in there is sort of not available, but it's still this kind of manipulation of the galaxy, how they compare to each other.
Senia, were all of your BIs and DIs non-negative?
No. Let me here, right? If you look here,
Yeah.
that one is -1. But that might trying to think. That might be, in fact, the only. In fact, that should be the only exception, because there's the linear relationship, and these coefficients are growing linearly, which means that the DIs can't be too small.
Right. So that would come from the 2.5 conjecture.
Yeah. Assuming that is true, then yeah, this should be the only exception.
AI and CI are always different by 1?
They're well, right, DI and CI
No,
are very,
I'm asking about AI and CI.
Oh, AI and CI, yes.
That should be just from the structure, right?
so you know that it can't. None of these intervals can be longer than length x.
Yeah.
Because that would give you two ways to write something down. Now, right. So there's only two possibilities. Either it goes up by 1 or it goes up just by 0. Now, the weird thing is that there don't seem to be any cases where it would be something like 2x plus 2, 2x plus 3, 2x plus 4, something like this. It does seem to be that if it's not an interval, then it's just
A singleton.
a singleton, exactly. And I don't think that there are, I mean, maybe there's like one counter example to that somewhere far down there.
So you have the 25x term there, which is just two numbers.
25. Oh, no. Oh, yeah. There it is. There's the one. Yep. There's your counter example. But I think if this happens, it happens very, very, very rarely. Maybe only finitely many times.
So you started off with this Ulam sequence. And
Yes.
for some reason, some guy started looking at the histogram of the terms mod lambda,
Yes.
or some lambda.
Yes.
Why? So how often does anyone, given some strictly increasing sequence of integers, feel like choosing random numbers lambda and looking at these histograms? That seems like a weird thing
madness.
to do.
So there's a method to the madness. So these were the original pictures that led Stefan to coming up with this. So what did he do? He had this idea that what you should do is you should think of the Ulam sequence as the Fourier coefficients of some smooth function. So what he did was he said, all right, well, let's look at the first 1,000 Ulam sequence terms and look at cosine of a n x, sum over those where a sub n is the nth Ulam term, right? And then you plot this from 0 to 2 pi, right? Now, you get spikes at 0 and 1 because that's where these exponentials line up. Everywhere else, you usually expect to just see noise, except in the case of the Ulam sequence, you find spikes, right? I mean, this is not, this idea is not so unusual. This is your circle method type of argument.
Fourier analysis tool, yeah.
Yeah, exactly. This is just circle method, except for the circle method, you expect to see spikes around rational numbers with small denominator. And here that's not the case. This is something different. This is something new.
All right. And this Ulam sequence itself.
Yes.
It doesn't have, I mean, like Gauss is supposed to have said about Fermat's theorem that there are lots of hard problems he can invent and they're not particularly interesting. So this Ulam sequence, you don't know why Ulam was interested in it, or even if he was interested in it, it was just a problem. I mean, is there any inherent interest in the sequence, or it's just a sequence and people start to look at it?
I don't know of any inherent reason to look at this specifically. I will say that at least some of these phenomena seem to be at least a little bit rigid. I mean, like robust. Like you could, from what I know, you could say alter the definition of the Ulam sequence. Say, oh, I don't want to consider everything that can be written down in exactly one way. Maybe I want it to be everything that can be written down in at most 2 ways, something like this. And I think all of the same phenomena are still true, probably, I would need to double check. I don't know. I don't think anyone has done like a good good search to see like how much you can alter these conditions and still retain this this basic property. I will say that the rigidity phenomena that we discovered, that seems to be much more general. We don't understand why, but there seems to be lots of other integer sequences where you get similar things. Things like Sudan sets. And why? I don't know. I'd like to know.
Other questions for Senia?
Well, you said these coefficients are very structured. Do you know more? Are there more regularities that you haven't mentioned? I mean, do you have any
Well,
asymptotics of AK as a function of K?
yeah. Well, let's see. I can maybe show you some pictures. Hold on, 1 second. 1 sec. And Ulam sequence of linear integer polynomials. So there it is. Okay, right. So numerical results. Okay, seen this. Okay, there we are. So what can you do? You can look at these coefficients modulo this magic polynomial. You're going to get 4 different histograms, right? For the 4 different coefficients. And this is the sort of thing that you get. There seems to be
Oh, your slide hasn't changed if you're showing a different slide.
Oh, okay. Let me stop share and do this. Let me do this. Hopefully.
That's it.
Now it works? Okay, good. Right? So this is, let's see, sigma I1, sigma I2. Let me just try to remember. Right. So this is long intervals. So this is an interval of length about x. Sigma I1. Ugh. Sorry, it's been a while since I've looked at this. But no. The point is that you can do these. Reduction modulo the magic polynomial, and you still seem to get these nice pictures. The one thing I will note is that one of the reasons why I haven't included this in the presentation is that I don't feel like I have quite enough data yet. You can see from just like how blocky some of these are, because the things occur only infrequently in some of these. Right, black lines at the magic number divided by 3, blue lines at guesses at where these histograms cut off. The point is, like, I can see that there is some structure. I don't know what that structure is.
But whatever it is, it's very similar to the structure observed in the original sequence.
Right. Yes.
Same type of thing, presumably, somehow.
Yes. Yes. I will also, there's other things, like, for example, right. For example, this is one of the things I know. Long intervals in U1x seem to occur almost exactly 4 times as often as. So by long, I mean that it's of length of about x, and short ones, I mean like a singleton. So the long ones occur 79.9.8% of the time, and short ones appear 20.02%, which almost feels like maybe it is exactly 4 times And then just because I've only cut it off at some finite point, that I see something different. It's just lots of stuff like this, where I would speculate more, but I would like to be able to compute, like, I don't know, millions of intervals before I really really guessed anything. So.
Okay. Other questions?
Is a document with these histograms and stuff put up anywhere?
Yes, this is. I mean, this is published. I just pulled up the overleaf because it's the
Oh, okay.
fastest way to
Yeah,
find
the
this.
easiest
But
to grab.
no, so this is a paper. If you look for Sheydvasser and then integer polynomials Ulam in some order, it'll come up. It's a journal. It's in the Journal of Integer Sequences. So you can find it and see all of this data and go through.
Other questions, comments? If not, thank you, Senia, for a very, very interesting talk. It's lovely.
Thank you.
Yes.
All right. Well, take care, and I'll see you around.
Okay, see you. Be well.
Thank you.
Right.
Thank you. Bye.
Good to see you.
Mhm.
Thank you, Mel.
Ah,
Thanks, Mel. Interesting talk.
yes, very much. Are you in Germany now?
Yes. It's late at night here. It's like 5 minutes after 10 or something.
Right, yeah.
Good to see you. Yeah.
Yeah. Okay, be well. Take care.
Okay.
Where are you, Kevin? New York or Florida or somewhere in between? Oh, you're muted.
Yeah, I'm in Miami.
Oh, okay.
Wednesday was a CUNY Monday, so all my
It
classes
was.
were online this week.
No, Wednesday was, yeah, that's right. Yeah, yesterday was class for me.
Yeah, so my Monday classes are online, and since yesterday counted as a Monday, yeah.
All right, I'm going to take off. Be well, everyone. Maybe see you next week.
Absolutely.
All right, bye-bye.